Review for index and classification properties of soil. This is not actually the entire discussion about index and classification properties of soil, since for sure you had taken up this topic already in your previous subjects before, mainly in your soil mechanics. This is only a review of what you've learned already. So, why we need to learn about index and classification properties of soil in relation to this course in foundation engineering? Talking about foundation engineering, it deals with the application of soil mechanics and rock mechanics in the design of foundation elements of structures. Of course, all foundation elements of every structure that you will soon design will be put on the ground, and this ground is what has been considered in your discussions in soil mechanics. How odd or weird your structure design could be, your structure platform is always through the ground. It could be a soil, rock, river, or ocean, but still to reach the Earth's crust. As a civil engineer, it's impossible for your structure foundation to be floating, because if so, then we should be taking another topic, not foundation engineering. Getting back to index and classification properties of soil in relation to foundation engineering, theoretically, shear strength is the most important geotechnical property of soils. It helps in stability of your structure foundations. By knowing the index and classification properties of soil, then it will lead us to better understanding of the soil indicative resistance to erosion or ground failure. By doing so, it will make our foundation design safe and stable. So based on the notes that you had already, here is the soil classification basics, commonly based on grain size and soil consistency. Several classification systems exist. Number 1, Unified Soil Classification System, or what has been known as USCS. ASTM D2487-11. Number 2, the American Association of State Highway and Transportation Officials, or AASHTO, ASTM D3282-09. Number 3, U.S. Department of Agriculture, or the USDA. Number 4, Bormister Soil Identification System. Number 5, Massachusetts Institute of Technology, or the MIT. Then for soil grain sizes, here is the grain size range in mm for gravel, sand, silt, and clay. So we have 4 soil types here. And with the USCS symbol, gravel stands for, or G stands for gravel. With a grain size range in mm under USCS 76.2 to 4.75. But in ASH2, it is 76.2 to 2 mm. And in USDA, it is greater than 2. While in MIT, it is greater than 2 also. For sand, USCS symbol is S. Then the grain size range in mm in USCS is 4.75 to 0.75. Then for ASH2 is 2 to 0.075. Then for USDA is 2 to 0.05. Then in MIT is 2 to 0.06. In silt, USCS symbol is M. It has the same grain size range with clay, or with the symbol C. For USCS, grain size range is fines less than 0.075 for the two soil types, silt and clay. However, they have already different grain sizes when in terms with AASH2, because in silt, the grain size range is 0.075 to 0.002, while in clay, the grain size range is less than 0.002. But basing in USDA, silt has a grain size range of 0.05 to 0.002, while in clay is less than 0.002. And basing in MIT, silt has a grain size range of 0.06 to 0.002, while clay is less than 0.002. And this is determined by mechanical analysis, example, sieve and hydrometer analysis. I believe that you had performed previously a mechanical sieve analysis. Then these are the sieve numbers and the type of soil that will go through it. Here are the sample sieve if you'll be doing mechanical sieve analysis. The first one is that if you're going to put your soil sample in a sieve 3/8 inch in diameter, then underneath of that is the sieve number 10, then underneath of that is the sieve number 40, then lastly underneath is sieve number 200. Then you will get this soil sample and with their grain sizes. First is you will get the medium gravel, and then what will go through the 3/8 inch sieve is the fine gravel, and then what will go through the number 10 sieve is the medium coarse sand. Then what will go through the number 40 sieve is the silt. Then lastly, what will go through the number 200 sieve is the dry clay, or what has been known as kaolin. Actually, here's a list of commonly used standard sieve sizes as per ASTM E11-09E1. So we have the sieve numbers 3/4 inch, and then opening in mm is 19, opening in inches is 0.75. And this is what has been considered as gravel. Next to that is the soil type considered as coarse sand, with a sieve number that starts from number 4, then number 6, then number 8, then number 10. And for number 4, you can see there the opening in mm and opening in inches. Next soil type, and then it will follow for the sieve number 6, sieve number 8, and sieve number 10. And then the next soil type is medium sand, which falls under sieve numbers 10 to number 40. So the next numbers are number 10, number 16, number 20, number 30, and number 40. And you can see there their corresponding opening in mm and in inches. Then the next soil type is fine sand, which falls under sieve numbers 40 to number 200. And these are number 40, number 50, number 60, number 80, number 100, number 140, number 170, and number 200 with their corresponding opening in mm and in inches. And lastly is the silt or clay, which is less than number 200, and this is number 270 with its corresponding opening in mm and in inches. And here is the particular angularity and roundness as defined by FHWA and HI-06-088, or the Federal Highway Administration is a division of the United States Department of Transportation that specializes in highway transportation. So, particular angularity or roundness, angular particle are those that have been freshly broken up and are characterized by jagged projections, sharp ridges, and flat surfaces. Subangular particles are those that have been weathered to the extent that the sharper points and ridges have been worn off. Sub-rounded particles are those that have been weathered to a farther degree than subangular particles. Rounded particles are those on which all projections have been removed, with few irregularities in shape remaining. Well-rounded particles are rounded particles in which the few remaining irregularities have been removed.